Today we're on lesson 2 of Unit 10, solving higher degree polynomial equations. We'll be covering pages 263 to 265, and you should have your calculator. Higher degree polynomial equations, remember the degree is the value of the highest exponent. There are equations where the variable is cubed to the fourth power or higher. An example would be this. Some of these equations, including the one in this paragraph, required advanced factoring techniques to solve. The ones we will be working with in this course can all be solved using the techniques we have already learned and applied in solving quadratics, including factoring, the quadratic formula, and incomplete quadratics. What is the maximum number of solutions for a linear equation? A line, only one solution. A quadratic, 2 solutions. A cubic equation, 3 solutions. A quartic, where the highest exponent is 4, would be 4 solutions. How can we generalize the maximum number of solutions to a polynomial equation? The maximum number of solutions to a polynomial equation is equal to the degree of the polynomial. So if the highest degree is 3, then there's a maximum of 3 solutions. The following 3 situations summarize the different methods we'll be using. First, a GCF. We've already done questions like this. First thing you always do is put it in standard form where you have 0 on one side and all the terms on the other. And your exponents, remember, you want them to go in descending order. Take out a GCF, then factor the resulting trinomial in parentheses into the 2 binomials, and then set each factor equal to 0, solving for x. Remember, if any of your new equations is a quadratic, you can use the quadratic formula or complete the square. Of the form ax to the fourth plus bx squared plus c equals 0. Okay, so this is fairly new to us, but let's take this example here. Putting it in standard form, x to the fourth minus 13x squared plus 36 equals 0. Notice the equation is similar to x squared minus 13x plus 36 equals 0, which can be factored into x minus 9 times x minus 4 equals 0. So if we simply replace x with x squared, we end up with this trinomial here is equivalent to the 2 binomials, x squared minus 9 times x squared minus 4. Then we can set each factor equal to 0 and solve accordingly. In this case, getting x squared by itself and then taking the square root of each side. So this method would work with trinomials of the form ax to the fourth plus bx squared plus c. Next, factoring by grouping. We've used this method before. So we have the 4 terms we split, and it ends up factoring into x plus 3 times 5x squared minus 2. Set each factor equal to 0. This incomplete quadratic, solving it for x, we get x is equal to plus or minus the square root of 2/5, and x equals negative 3 is our other solution. So again, there were 3, the highest exponent here was 3. There were 3 real solutions. Here, the highest exponent 4 solutions. Here, the highest exponent was 5, and there were 3 real solutions. Again, the maximum number of solutions would equal the degree of the polynomial. So we would have a maximum of 5 solutions, but we could have less, as we did in this first example. Okay, solving polynomials of higher degrees takes practice and creativity. They could always be checked on a graph as long as the solutions are not imaginary, or if you have irrational solutions, then we would simply have to look at the decimal, a rounded value of the decimal. Look at 1. Where would the graph of y equals 5x to the 5th plus 20x to the 4th plus 14x to the 3rd intersect the x-axis? Well, if we go back and look at number 1, it would intersect the x-axis at -3, -1, and 0. Where would the graph of y equals, so this is from the second example, it would intersect at -3, -2, 2, and 3. And the graph of y equals 5x to the 3rd plus 15x squared minus 2x minus 6, it would intersect the x-axis at -3. And then it's asking us to take the rounding to the nearest tenth of the square root of 2/5. Negative square root of 2/5 is approximately -0.6, and positive square root of 2/5 is approximately positive 0.6. And the squiggle equals is approximately. Okay, so here we go. Solve each of the following equations algebraically. It's already in standard form for us. There's 3 terms. Is there a GCF? Yes, there is. X. Factor out x, and we get x to the 4th minus 10x squared plus 21 equals 0. Now the trinomial inside parentheses, leading coefficient is 1. What are the factors of positive 21 that sum to -10? -3 and -7. So this factors into 2 binomials. Instead of being x minus 7 and x minus 3, it's x squared minus 7 and x squared minus 3. So that when we multiply x squared times x squared, we will get x to the 4th. Bring down the GCF x. Set each factor equal to 0. And now solve individually. Add 7 and take the square root of each side. X equals plus or minus the square root of 7. Add 3 and square root of each side. X equals plus or minus the square root of 3. So here we have 5 solutions, 0, plus or minus 7, and plus or minus the square root of 7, and plus or minus the square root of 3. Number 2, it's already in standard form. There's nothing common to all 3 terms. Sorry, 4 terms, so this is grouping. X plus 3 times x squared minus 1 are our 2 factors. Set each factor equal to 0. Or you could have taken x squared minus 1 and factored it further if you like. Subtract 3, x equals -3. Add 1, divide by 2. Sorry. Add 1, then take the square root of each side. x equals plus or minus 4. We have three real solutions, -3, 1, and -1. Does the order in which you write these matter? No. We're using solution set notation there. Okay, next. Number 3, let's put this in standard form. Our highest exponent is 4 here with a leading positive x coefficient, so keep this where it is. Bring these two items over to the left-hand side. X to the fourth minus 29x squared plus 100 equals 0. Three terms, factors of 100 that sum to -29, -25, and -4. This will factor into two binomials. Instead of x minus 25 and x minus 4, we want x squared minus 25 and x squared minus 4. Set each factor equal to 0, or you could factor further. These are both difference of perfect squares. I'm going to keep them as they are and set each equal to 0. And then solve our incomplete quadratics, right? This is an incomplete quadratic. Add 25 to both sides, and then square root each side. X equals plus or minus 5. Add 4. Take the square root of each side. X equals plus or minus 2. 4 real solutions. -5, +5, -2, and +2. And you're certainly welcome to pause the video and try some on your own if you like. Okay. It's already in standard form. There's definitely a GCF. Looks like it's 5x. Taking 5x out, we have x to the fourth minus 12x squared plus 332. Inside parentheses here, we have three terms, a trinomial. Factored, leading coefficient is 1. The factors of 32 that sum to -12, -8, and -4. That's an x to the fourth. So when we write our two binomials, we would like to write x squared minus 8 and x squared minus 4. Bring down the 5x and r equals 0. And now set each factor equal to 0. Dividing by 5, x equals 0. Adding 8, x squared equals 8. Square root each side. X equals plus or minus. Simplifying that, I'm thinking 4 times 2 is 8, and the square root of 4 is 2. So 2 square root of 2. Adding 4 to both sides, and square rooting. X equals plus or minus 2. Same here, we have, this was degree 5. The highest exponent was 5, and we do have 5 real solutions. 0, plus or minus 2 square root of 2, and plus or minus 2. Number 5 is already factored for us. So let's just take each factor and set it equal to 0. Subtract 9, x squared equals -9. Square root each side. X equals plus or minus 3i. Subtract 3 from both sides here, x equals negative 3. So we have 3 solutions, 1 real and 2 imaginary. 1 real solution and 2 imaginary solutions. So this here, if we were to look at this graph, it would cross the x-axis at only negative 3. Number 6, there's a GCF. Let's take that out. X to the 4th minus 10x squared plus 9 equals 0. The trinomial inside parentheses. Leading coefficients 1. The factors of 9 that sum to negative 10, negative 9 and negative 1. And that x to the 4th, so we want x squared minus 9 times x squared minus 1. Bring down the GCF x, bring down the equals 0. Please keep in mind again, at this point I could set each factor equal to 0, or in this case I'm going to factor them further. These are the difference of perfect squares. Right? X plus 3, x minus 3, x plus 1 times x minus 1. And now we have 5 factors, set each factor equal to 0. Or if you preferred, you could have set this equal to 0 and then solve each incomplete quadratic, as they did similarly to others. Alright, so we do have 5 solutions, 5 real solutions: 0, negative 3, positive 3, negative 1, positive 1. Number 7. 4 terms. There is no GCF to all 4 terms. So 4 terms we know we split. And we have x squared comes out, 2x minus 3 plus 1, 2x minus 3. 2x minus 3 times x squared plus 1 equals 0. Set each factor equal to 0 and solve. Adding 3, dividing by 2, subtracting 1, and then square rooting each side. Plus or minus I. So we have 3 solutions, 2 imaginary, 1 real. And number 8, it's already factored for us, right? So we set each factor equal to 0. Alright, so this is an incomplete quadratic. We just add 9 to both sides and then take the square root. And x equals plus or minus 3. This trinomial, leading coefficient is 1. Go to the constant. There are no factors of 1 that sum to 4, so we have to use the quadratic formula or complete the square. And I think you all know what my preference is. In this case, leading coefficient's 1. The coefficient of x is even, so I'm going to use complete the square. X squared plus 4x plus blank equals negative 1 plus blank. what belongs in each blank. It's 4. So we have x plus 2 squared equals 3, and now square root each side. Square root of 3 doesn't simplify. Subtract 2, x equals negative 2 plus or minus the square root of 3. So we have 4 real solutions here. We have plus or minus 3 and negative 2 plus or minus the square root of 3. And yes, you could check these by putting them into the graphing calculator. I'm just going to go back to number 6 and check this. What does this look like? So I've keyed in the our polynomial expression, the left-hand side of our equation here. Press graph. And there we have zeros or x-intercepts of, this is negative 3, this is negative 1, this is 0, positive 1, and positive 3. Once again, thank you for your attention.